A telescope captures something impossible. An object from another star system develops a tail, then appears to lose it, then grows it back, longer and brighter than before. All observations in this video are based on publicly available telescope data. Astronomers across 6 continents watch their screens in silence. No one speaks, because what they're seeing shouldn't happen. Not like this, not this fast. What would you do if you were the first person to see this? Let's go back to the moment everything changed. February 2025. A graduate student in Hawaii is reviewing routine images from pan-stars. Automated alerts flag something unusual. An interstellar visitor, designated 3I Atlas, has been crossing our solar system for months. But tonight, something is different. The tail appeared faint, almost invisible. She zooms in, adjusts the contrast. Nothing helps. The tail that had been clearly visible just weeks earlier seemed to have faded dramatically. She messages her supervisor. Within hours, observatories worldwide pivot their instruments toward the same coordinates. Everyone wants to see the vanishing act. Because here's what makes this moment extraordinary. Comets rarely lose their tails without reason. They follow predictable patterns of sublimation, solar heating, and particle release. But 3I Atlas is not from here. It came from a star system we may never identify. It formed in conditions we can only guess at. And now, millions of kilometers from Earth, is behaving in ways that challenge our assumptions. The tail appeared to fade to near invisibility over a period of a few days. Some researchers began drafting papers about potential fragmentation. Others suggest the object might not be a comet at all. Then, 3 weeks later, new images arrive. The tail has returned. Not just returned, it's longer, sharper, more structured than ever before. Comment what you think is happening, even one word. Let me show you what the data reveals. Where scientists disagree, we present mainstream interpretations. When astronomers say a comet tail disappeared, they're describing a specific optical phenomenon. The tail didn't physically detach. It didn't explode away into space. It became invisible to our instruments. Here's why that matters. Comet tails are not solid objects. They're streams of dust and ionized gas pushed away from the nucleus by solar radiation and solar wind. The visibility of these tails depends on 3 critical factors. First, the angle between the observer, the comet, and our star. When we view a tail edge on, instead of from the side, it appears dramatically thinner. Think of looking at a sheet of paper from its edge versus from above. The width collapses to nearly nothing. Second, the brightness of the coma, the cloud of gas and dust surrounding the nucleus. If the coma dims, the tail feeding from it dims proportionally. Without fresh material being sublimated from the surface, the existing tail gradually disperses. Third, the scattering properties of the dust itself. Some dust grains reflect sunlight efficiently, others absorb it. The composition of 3I Atlas determines how much light reaches our telescopes. But here's where the story gets complicated. The newest images show something unexpected. The tail isn't just visible again. It displays multiple streamers, layered structures that suggest different velocities of particle ejection. One streamer extends over 400,000 kilometers. Another curves at a different angle, indicating a separate source region. The brightness has increased by a factor of 3 compared to pre-disappearance observations. Virtual Telescope Project in Italy captures the sharpest images yet. The tail shows fine details, wispy structures that hint at complex processes beneath the surface. Multiple observatories confirm the brightness changes independently. These are not imaging artifacts. This is real evolving activity from an object born around another star. So here's my question for you. A equals natural phenomenon, fully explainable by known physics. B equals something unknown, requiring new understanding of interstellar objects. C equals we need new physics entirely. Comment A, B, or C. No wrong answers. Now let's talk about what science cannot fully explain yet. The speed of the change. Comets typically show gradual variations in tail visibility. As they approach or recede from the warmth of our star, sublimation rates increase or decrease predictably. But 3I Atlas appeared to go from highly visible tail to near invisibility in under 4 days, then reignited to maximum brightness in less than 3 weeks. That's not gradual, that's abrupt. Several hypotheses attempt to explain this behavior. The first involves jet activity. Comets are not uniform spheres of ice. They're chaotic aggregates of frozen volatiles, dust, and possibly rocky material. Pockets of highly volatile substances can hide beneath thin crusts of less active material. When solar heating reaches a critical threshold, these pockets rupture. A jet erupts. Suddenly, tons of material per second blast into space. The jet creates a localized bright spot on the nucleus and feeds a new streamer into the tail. But here's the twist with interstellar comets. They formed in different temperature and pressure environments than objects from our own Kuiper belt. Their composition might include volatiles we rarely see, substances that sublimate at unexpected temperatures. Carbon monoxide ice, for example, becomes active much farther from our star than water ice. If 3I Atlas contains pockets of exotic ices, it could produce jets that turn on and off as different regions rotate into sunlight. The nucleus might be tumbling, not spinning smoothly, but wobbling chaotically. This would expose different hemispheres to solar heating on unpredictable cycles. Imagine a cosmic rotisserie, but one that spins in 3 axes simultaneously. A jet on the currently illuminated side fires intensely. The tail brightens. Then rotation carries that jet into shadow. Activity stops. The tail fades. Hours or days later, a different region faces our star. A new jet activates. The tail reappears, possibly with different geometry. This is not just speculation. We saw hints of this behavior with Borisov, the second confirmed interstellar comet. Borisov showed outbursts, sudden increases in brightness that suggested localized jet activity. But 3I Atlas is giving us something Borisov didn't. Repeated cycles of visibility change. Which brings us to the second hypothesis, fragmentation. Not catastrophic disintegration, but gentle crumbling, small pieces breaking off the main nucleus. Each fragment carries frozen volatiles that immediately start sublimating in the unfiltered solar radiation. Suddenly, you have multiple sources of gas and dust. The tail structure becomes more complex. Streamers appear at different angles because they're being fed by fragments following slightly different orbits. Then, those fragments either sublimate completely or their volatile content exhausts. The extra tail structures fade. We're left with the primary nucleus and whatever volatiles it continues to release. Astronomers are watching carefully for any signs of discrete fragments in upcoming observations. The third hypothesis involves solar wind dynamics. The solar wind is not constant. It fluctuates in density, speed, and magnetic field strength. Sometimes our star releases coronal mass ejections, massive bursts of plasma that race through the inner solar system. When these events strike a comet, they can dramatically enhance tail visibility. The increased particle density pushes dust farther from the nucleus. The magnetic fields energize ions, making them glow brighter. But predicting these events is difficult. Space weather remains one of the great challenges of solar physics. We can observe the surface of our star, but translating those observations into accurate forecasts of particle arrival at specific locations requires complex modeling. Did 3I Atlas encounter a solar wind enhancement that reignited its tail? Possibly. Space weather monitoring satellites did record increased activity during the relevant period. But correlating that with the specific geometry of 3I Atlas's orbit requires detailed calculations that are still ongoing. Does this change how you see our place in the universe? Let me take you somewhere bigger. Forget the technical details for a moment. Think about what we're actually witnessing. An object formed billions of years ago around a star we cannot name, in a region of space we may never visit. It was shaped by the conditions of that ancient stellar system, the temperature of its birth cloud, the composition of the protoplanetary disk, the gravitational influences of planets we will never see. Then something happened. A near collision with another star, a gravitational nudge from a giant planet. Some event we cannot reconstruct from the evidence available. 3I Atlas was ejected, thrown out of its home system at speed sufficient to escape that star's gravity entirely. For millions, perhaps tens of millions of years, it drifted through the interstellar void, the space between stars where temperatures approach absolute zero, where radiation comes only from the faint cosmic microwave background and distant galaxies. It crossed light years alone. And then, by pure chance, its trajectory intersected our solar system. Not a capture, just a hyperbolic pass. It will swing past our star, gain a tiny bit of speed from the gravitational interaction, and continue on into the galaxy, heading toward another encounter in another era with another star. We have this moment, this brief window measured in months, when 3I Atlas is close enough for our instruments to see, to measure, to photograph. And during this window, we're watching it wake up. Solar radiation heats its surface for the first time in eons. Frozen volatiles that have been dormant since it left its birth system begin to sublimate. Gas escapes, dust follows, a tail forms, but the composition is alien. Not alien like extraterrestrial intelligence, alien like foreign, different, formed under conditions our solar system never experienced. When we analyze the light reflected from that tail, we're seeing the chemical fingerprint of another star's planetary system. We're reading a message written in ice and dust that traveled across the galaxy. That's why the changing tail matters so much. Each phase of activity exposes a different layer of material. The surface composition might differ from layers just beneath it. If 3I Atlas is like the comets in our Kuiper Belt, it's stratified, built up from icy grains that accreted over thousands or millions of years. Early layers formed in one era of its birth cloud. Later layers formed when conditions changed. Now, solar heating is peeling back those layers. The initial tail showed us the surface composition. The disappearance might have marked the exhaustion of the most volatile surface ices. The reappearance with greater brightness could indicate we're now seeing deeper material, ices that were protected by the outer crust, material that has been hidden from any radiation or heat source for the entire lifetime of this object. We are watching an archaeological excavation conducted by sunlight, and every observation, every spectrum, every photometric measurement adds data that might survive in our archives for centuries. Because 3I Atlas will not return. Its orbit is unbound. After it rounds our star and heads back toward interstellar space, it will never cross our system again. This is our only chance. Write one sentence, this means. So what happens next? Observatories are tracking 3I Atlas continuously now. The Virtual Telescope Project has scheduled weekly imaging sessions. Pan-STARRS maintains automated monitoring. Amateur astronomers with high-resolution equipment are contributing observations that sometimes rival professional facilities. Everyone wants to catch the next change. Because if the pattern continues, we might see another fading phase, another regrowth. Each cycle would give us additional data about the nucleus composition, rotation state, and volatile distribution. But there's also the possibility of fragmentation. If 3I Atlas is structurally weak, the thermal stresses from solar heating could pull it apart. We've seen this before with comets from our own Oort cloud. Objects that survived millions of years in the deep freeze but shattered within months of approaching our star. If fragmentation occurs, we'd see multiple nuclei. Each fragment would develop its own coma and tail. The complexity would increase dramatically. Or we might see the opposite. The tail could fade permanently as the most active regions exhaust their volatile inventory. 3I Atlas could transition from an active comet to an inert, rocky body. Just another asteroid-like object on a hyperbolic trajectory. The window is closing. 3I Atlas reached its closest approach to our star in mid-January 2025. It's now moving outward. Every day it travels farther from the heat source that drives its activity. Within months, it will be too distant for detailed observations. Within years, it will leave the inner solar system entirely. Within decades, it will cross the heliopause, the boundary where our star's influence fades and true interstellar space begins. And then it will vanish into the darkness between stars. But here's what keeps astronomers awake at night: the unknown variables. We don't know the rotation period with certainty. We don't know if the nucleus is a single body or a contact binary. We don't know the exact composition of the volatiles producing the tail. Every one of these unknowns affects our predictions. If 3I Atlas is tumbling chaotically, we might see activity patterns that seem random but are actually determined by complex rotational dynamics. If it's actually two objects in contact, like a cosmic snowman, the structural stresses could separate them at any time. If the volatiles include species we rarely encounter, the sublimation behavior could surprise us right up until the object becomes too faint to observe. This is the reality of studying interstellar visitors. We get no advance warning, no time to prepare ideal observation campaigns. They arrive, they pass through, they leave, and we scramble to gather whatever data we can before the opportunity vanishes forever. We've only confirmed 3 interstellar objects so far. Oumuamua in 2017, cigar-shaped or disc-shaped, depending on which models you trust. No visible tail. Acceleration that couldn't be explained by outgassing alone. Borisov in 2019, classic comet behavior. Water vapor and dust producing a normal-looking tail. The most similar to our own comets of any interstellar visitor yet discovered. And now 3I Atlas. Somewhere between Oumuamua's mystery and Borisov's familiarity. Active like a comet, but with behavior patterns that remind us how little we actually understand about objects from other stellar systems. Each visitor teaches us something new. Oumuamua taught us that interstellar objects might not look like what we expect, that our assumptions about comet tails and rocky asteroids might be too narrow. Borisov taught us that some interstellar objects are remarkably similar to our own comets, that the physics of ice and dust might be universal. 3I Atlas is teaching us about variability, about how interstellar comets can show dramatic changes on short timescales, about how a single object can display multiple activity phases during a single passage through our system. But it's also teaching us humility, because despite our sophisticated telescopes, our spectroscopic analysis, our orbital mechanics calculations, we still can't predict with certainty what this object will do next week. The universe is not obligated to make sense to us. It operates according to physical laws we're still discovering, in regimes we've barely explored, with materials and conditions we can only approximate in laboratories. 3i Atlas is a reminder that there is still mystery, still unknown territory, still phenomena that will surprise us. So tell me, what do you think happens next? Maybe we've been asking the wrong question. We want to know what 3i Atlas is, where it came from, what it's made of. But perhaps the deeper question is what it represents. Every interstellar object that passes through our system is proof that the galaxy is not static. Stars are not isolated. Planetary systems exchange material across light years of space. The building blocks that formed our own world might have included grains from other star systems. The water in your body might have originated in a cloud around a star that died before our own was born. We are not separate from the galaxy. We are part of it. 3i Atlas is a messenger from that larger reality. A reminder that the universe is vast and old and full of objects that dwarf our human timescales. It's been traveling for longer than our species has existed. It will continue traveling long after we're gone. And somewhere, millions of years from now, it might pass close to another star. Another world with beings capable of wonder might point their instruments at it and ask the same questions we're asking now. What is this thing? Where did it come from? What can it teach us? The unknown is not a void. It is an invitation.